Yeah, so my second last lecture. I'm sad. I'll be more sad next week. Yeah, so it's just started on section 3. You guys got homework coming up soon. I'm gonna have to make a small apology that I have to run off at the end of this lecture. So if you have questions, make it rapid fire. Happy to answer a few, but I have to run away. Yeah, okay, cool. Weird black blob coming up on my screen. Okay, so we ended section 2, made a start on section 3. Hopefully that was useful for you guys. I will get back into it. We're up to the fun stuff of numerics. So my background, applied mathematics more than pure mathematics, because I'm interested in that. So this is like my area. I love this stuff. I love differential equations. I always have. Yeah, so this is fun stuff. Floating point and the problems you get. So hopefully we'll cover that today. Do a little bit about, we talked a little bit about, you know, here's some files you're gonna have to deal with. Binaries, yeah, cool. CSV files, you'll see a lot of those if you end up in the data science area. Just because it's kind of funny, it's like probably the most successful programming language is Excel. It's like people don't think of it that way, but everyone's got a copy of it and everyone can use it. And so if you say how useful something is by how many people are using it, it probably wins. Cool. So that was data frames and CSVs. Data frames will come back later on. Kind of this tabular data format is super common in machine learning. It's like basically the default data type that you're going to be dealing with, and all the good methods work on tabular data and images. JSON files, you guys, everyone having fun with the homework, digging through JSON files? Not so much fun. You're having fun. It's interesting. It's like, this is like, you have a little experience of this now. This is kind of what it's like digging into someone else's code, is digging into someone else's data without having an idea of the structure of the data format. Later on, you guys will get to, part of this course, you get to dig through someone else's, maybe if they do run it the same way as last year, you'll get to have a look at what it's like to edit someone else's code rather than starting from scratch, which is actually the normal case if you're working in software professionally, is you've got an existing thing that you've got to add to, remove stuff from. So if it seems painful, it kind of is, but you get coping strategies. Git is one of them. Cool. Any little questions about that stuff, like anything that's come up? If you want to ask a question now, it's probably a good time. Are you happy? Take it as happy, quiet, it's happy. Okay. I don't know how much to say about this stuff because I sort of want to we've got to get through section 3 pretty quickly, but basic thing is using plots of, it's better than it used to be. And the story in Julia is much better than it used to be. It could be better still. There's some really cool stuff if you look at Makey. Is anyone, like one of the things, it's really common for people to get into doing software. Some of them just fall in love with doing visualizations. It's like, it's kind of a fun thing. If that's your bent, if you're a visual sort of person, and super important as a professional. So it's kind of, maybe you've sort of seen it in Amy's talk. There's kind of like 3 streams you end up with as a mathematician in industry. You can sort of be like deep in the guts of software, writing code at a very low level. Then you've got like an in-between bit of like an analysis-y bit, and then you've got like a customer front bit. There's sort of like that spectrum of like where you end up, as you can end up just being a consultant. So making cool visualizations to tell a story to people who are not sophisticated mathematically. I guess this is like, it's a weird lesson when you're young, is like not everyone's going to be as good as maths at you, even if you don't feel great at it now. You're actually well ahead of where most people are. Most people haven't touched it since high school. So if you tell us a story, communicating visually is like, it's like a superpower. It will really accelerate your career. I am not great at it. I could always improve. There's some examples of some basic plot functionality. I don't know how, what would I say is interesting here? The API, it's like, this is like one of these ones, I guess on a meta level, with your homework, you've got question 16, sorry. Has anyone had a go at that yet? Losing my voice. Yeah, so using someone else's API, learning an API is a big part of software. So learning how to drive someone else's software So you're not constantly reinventing the wheel is a big deal. So learning plots API, this one's sort of like inspired by matplotlib. It's a big library, this plots one. So you have lots of things here. So the typical things are like labeling colors, labeling limits, where you want the positioning of a legend as a symbol. All these are symbols coming in here, setting Y limits, blah, 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 blah. These are all like good visual examples of using the plots library. I won't belabor the point because it's like, there's nothing too much interesting here that I think you can't work out on your own by looking through. This one, I think this one's super useful, just the layout when you try and want to include multiple plots. So to be clear, P1, P2, and P3 are 3 separate plots. You give them a handle, this P1, P2, and P3, including them in the same plot and playing with the layout. That's like a super useful one to know. Like, do you want them across? Do you want them down? You give it a tuple to say. You can set sizes. We talked just a tiny bit about binary formats. If I get time tomorrow, I'll say a little bit about images. Like, big part of my career has been dealing with images as an array. They're basically an array. When you're doing plots, this is like dumb advice, but if like maybe later on you go and write a paper, choosing resolution of plots so they print well, please think about that. If you learn a bit about like the difference between something like a PNG, which is basically just an array of image data. So it has a fixed resolution versus a vector graphics format like SVG. These two things you've heard before. Maybe you would have seen them, maybe. Vector graphics, you can sort of infinitely zoom. They're really setting a polynomial in the plot. So like, or something like that, like this continuum that, so you can keep zooming in. So they're not a fixed resolution format. Whereas something like a PNG, if I do this one and I save the plot, I'll typically save it out as a PNG. So you've got this resolution that you're always stuck with and have to deal with. That's a thing to learn. That's a silly little lesson. I've got another example here of getting data from a HTTP request, reading it into a data frame. So we just showed this yesterday. I can do this if you want to see it again and again. It's a pretty typical pattern. It'll be slow because including all these big packages. Yeah, so get request from a HTTP API that will give you some data, typically into JSON, reading it into a buffer and then popping it out into a data frame. Oh no. So it doesn't have using. I didn't follow the notes exactly, so. So we'll go get this temperature data from here. This is from the Statistics with Julia book. So this is an example from the book. Has anyone gone and looked at Yoni's book for examples? It's a good source of examples. It's all on GitHub, I think. So that's cool. And then, so that was response and then data. Again, tabular data. Everywhere you go, you're going to get tabular data. That's just a little example of that. This is an example of reading data out of a data frame. So we're going to get the temperature in Brisbane, temperature in the Gold Coast, look at the difference between them as a function of dates. So this dates, you would not believe how problematic dates are and times are and time zones. And big one for me, again, one big part of my career is doing imagery and LiDAR. Another big part is dealing with GPS information, GNSS information. Leap seconds. Have you even heard of a leap second? This is like every couple of years, they decide to add or remove a second from the year to keep the year the same length or to keep the meridian in through Greenwich, whichever way you want to think about it. So this is like a committee forms and they go, okay, yeah, it's been speeding up a bit. We're going to better take a second out and we better put a second back in, and they'll publish these. So times are a huge problem in computing, even things like time zones, and you deal with Brisbane, we don't have daylight savings, so we have UTC time. Dealing with this stuff is a big thing in programming. It's not fun. I don't enjoy it at all, but it's a thing. They're talking about getting rid of leap seconds they keep threatening to do it. It should be great. It's very confusing. Anyway, data modeling is a problem. The Earth's not a perfect sphere spinning in space. It's wobbling around. It's actually squidgy and moves in and out. So I just say about using dates. So here's an example of formatting a date string. So there's ISO format, so International Standards Organization for dates. So this is an example of you driving the Julia library. This is just the dates, not the time part. So to turn, sorry, I went a bit fast and include. Inside the data, there's a field year, month, day. We're doing a comprehension over that through the data frame. N row for data is number of rows when you're dealing with a data frame. Hopefully you can see that. So you're going to parse this thing, this bit of data as an int as a year, parse this one as a month, parse this int as a day. Cool. And then you'll end up with a date string, and you can do operations on dates. Like you can add a day, iterate over periods with dates library. So you know, what do I want to say? So dates. You can do this sort of stuff. Hope I'm not lying. You can add a day, add 100 days, add 100 years. Cool. And then you get something that will be interpreted as a date. So it's a useful data type for dealing with date time information. So normal sort of stuff here that you'll be doing, you can make a histogram of the temperature differences, plot this kind of stuff. Another useful cool one is creating animations. Actually, one of the first things I did in Julia was make an animation just to see if I could work out how to drive it. So this is like, oh no, cancel. I didn't check the codec. Oh, that makes me sad. DLC. Okay, we'll see if that works. So this was me simulating wave equation, adding drops. This was just a little thing I did. I didn't have this cool animate macro. You guys did. So I have no sympathy if you're having trouble getting this to work. I had to make each of these frames an image and then use a program called FFmpeg to turn it into a video. That's how ancient it was. But I think it's cool. It's like, it's easy to do linear algebra in Julia. It's easy to turn a PDE into a linear system if you discretize it. You can get all these cool patterns. This was just a dumb thing I did. I don't even know why I did it, but there you go. You can make animations. Crazy stuff. I don't know why I wanted to show that, but I just did. So now, to show that things have improved, you can use this animation thing to make a little GIF, and that would have been a much simpler process to just do that than this horrible thing, filling up my hard drive with 2,000 PNGs. Yeah, so this is easy. You can also, has everyone discovered this macro, animate? That's another alternative way of setting this up rather than doing all this stuff here. So you've got this node, anim equals animation, add the frame. You can just put this macro at the start if you go anim equals add animate, blah, plug it in, you get the same kind of thing. So I find examples of that on the web. I just think it's useful to see, like maybe I've shown a few of these macros. It's not really clear what the hell they're for. It's really to avoid doing this little bit of extra work of like, I'm going to set this up and then I'm going to add a frame to the animation, blah, blah, blah. You can just do it in one go. It's much easier. And you can make cool stuff like this. I don't know, I like things like this. I like maths. Maths looks pretty. You get all these funny patterns. It reminds me of like Philip Glass for some reason, if anyone knows that. I don't know. I think there was an animation from Sesame Street when I was little with Philip Glass playing in the background. I like cool things like that. So it's like in the progress of making Julia, they've kind of pulled out a lot of the functionality into separate modules. Statistics is one of them. It's kind of a thing that used to be in base and they pulled it out, same as linear algebra. To give it that flavor of it's not really just for scientific stuff. It's a general purpose programming language. If you want to do this stuff, you should include it and do it. So as you'd expect, you know, you can do all your basic statistical summaries. So again, this is good for a reference. You've got all these different types of means and geometric mean, arithmetic mean, harmonic mean, variance, standard deviation, min, max, median, quantiles, blah, 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 blah. Easy, all that stuff's there for you. Just as a reference, I won't say more than 10 seconds on that. Okay, now we're getting on to fun stuff. So this is fun, I guess. I talked at the start, very first lecture, about integers and how they're represented in a computer. And I went, floating point's too hard at the moment. I'll push it out till later. Come back to it. It's not that hard. It's just a bit weird. The way this will go through is I'll say about like how floating point numbers are represented. Then I'll show you some weird stuff to do with that. What happens with that? And this stuff's super important. Like, I can't stress this enough that practically, as an applied mathematician doing numerics, worrying about floating point stuff is like a big part of my life. You'll get very strange errors and they come up all the time. So I'll just point at a few and you'll understand what's going on. It's kind of funny. The big thing to remember in your head is it's like, they're not really real numbers. They're kind of like, they're rational numbers pretending to be real. So you lose a few properties, kind of. They're almost real numbers. So you've got this problem that you've got a finite precision to represent, finite number of bits to represent a floating point number. So again, like I probably showed this in the first lecture, you've got float, which depending on your computer, sorry, that was, I said the wrong thing. Anyway, that was it only has the screen. Okay, you got all these different floats. You got a float 64, float 32, float 16, and you've got a big float. Based on your level of precision you need. So this is 16-bit float, 32-bit float, 64-bit float. It's a kind of a weird name, floating point, but maybe that'll be clear when you see what the representation is about. So this is a type for making a float 64 from X. And there's a mode which determines how it's rounded. So example here, rounding down, rounding up for pi. So again, you can't represent pi exactly. It's always this finite precision. You're going to get a number that's close to it. Now, floating point, I guess the big thing to say is it's like, if you think back, put yourself back 70 years in the past, 80 years in the past, and you think, how are you going to represent real numbers on a computer? I would never have come up with floating point myself. I think floating point is a little bit strange. I probably would have chosen, I haven't said what floating point is, so maybe I'll come back to this later, but I would have chosen something like logarithmically with a sign bit would seem like the obvious thing to me. If I want, one of the designs when you're trying to represent real numbers is you want a huge dynamic range. You want to be able to go to plus infinity, to minus infinity, you want to be able to represent, little atomic radii out to galaxies. This is the kind of stuff you want to deal with. So you need a huge dynamic range. So obvious, semi-obvious thing to me to do that would be logarithmically spaced. I'd go like, here's my number, I'm going to take the log of it and then put a sign, or the absolute value of that log. That's not what floating point is. Floating point is a little bit weird, and we can do it by pulling it apart a bit here. So pretty print float. Let's just try running this stuff and we'll see what we get. So there's these funny bits called a sign bit, an exponent, and a significand. Some different names for that stuff. I never remember what they are. So if we've got X, so what's the type of this guy? It's a float 64. So again, if I say, this is in the notes right next to me, if I say size of, that's going to be size in bytes, which will be divided by 8. Yeah, 8. Yep, cool. I can do this bit string function. Okay, cool. That's what it is. 64 ones and zeros. What do they actually mean? See how this pretty print float works. Let's see if it's actually pretty. So it has a sign bit of 0, has an exponent of 1000001, and a significand of blah 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 blah. Cool. You have these functions built in to exponent, if I can spell, is 3, and significand of x is 1 point. If you want these as floats. So again, always typing this weird function in, what does it actually is? So this is the other name. Sometimes this guy's called mantissa. I think in my head, I always going to go like, oh, significant, because I learned mantissa when I was young. Funny names. And Same for exponent. Exponent should be obvious. You know, it's the number it's raised to the power of. So maybe this gives you a hint about how these things are represented. So this will be a big hint, is if we do this guy, 2 to the power of the exponent, because I didn't type these things. Let's just do it long-winded. We get our number back. So this is the way they're actually represented. You've got 2 to the power of the exponent times the significand. Maybe that's a funny way of rearranging it. Maybe if you put the significand out the front, it'd be a bit more obvious. It's just a to the 2 to the, yeah, so significand to the times 2 to the power of the exponent in bits. So this is in bits. So you also get single precision. So all this was doing was just taking the bits equals a bit string of that. So it's just pulling these parts about. So what you'll see here is that the first bit is the sign bit. Second to 12 is the exponent. 13 to 64 is the significand for 64-bit floats. IEEE something or other standard. What is it, 70 something? I can't remember. I never remember the name. There's a standard for this. You also have a few special ones. If you're going to do a 32-bit float, so this is called like double precision, single precision for historical reasons. Older computers, 32 bits is enough. Then they went, oh, no, it's not enough. You need 2 of those, double precision. You need twice as many bits as that. Again, the thing to notice here is the first one's the sign bit, 2 to 9 is the exponent, significand is 10 to 32. So if we, again, I won't belabor this one because it's kind of boring, but you go through and you go like, oh, okay, x equals 15, blah, 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 blah. With that, this is setting up a float 32. Remember, maybe you remember this little signature you can put in to make it a float 32. Cool. So again, you get your number back if you do that. So what were they actually represented by? We get to do some equations. I'll just talk through these pretty briefly. Is that we have a sign bit. Now, interesting bit is we don't bother with like the numbers in this little floaty, the F bit, the significand. The bit representation is between 1 and 2. So you start with 1 and you go up. That's just a decision. It's all powers of 2. So you're just trying to pad all these numbers between powers of 2. One of the consequences of this, maybe that's obvious, maybe it's not. I got a picture of this, but I don't know if it's going to show very well because it's kind of a terrible picture. This is like a representation I stole off the internet of the spacings between floating point numbers. This is the bit that's weird. I would have thought logarithmically spaced would make sense. What they've chosen with floating point representation is that they're evenly spaced between powers of 2. So depending on how many bits you have in the significand, it's like how many evenly spaced bits you're going to get. Evenly spaced represented floating point numbers between powers of 2. It's kind of weird, right? Maybe not. Depends what you're used to. I think it's just interesting. Smarter people than me came up with this representation. Yeah, 2 to the d, if you have d power d, there's exactly 2 to the d evenly spaced numbers in the set. Okay. So the standard, that's the one. I could never remember it. If you want to get the details, IEEE 754. This is the one that's basically everywhere. You can go and read that. This is this thing. It's like, this should line up exactly with how we've cut up the floating point numbers before. You've got your first one's a sign bit, 11 bits for the exponent, 52 bits for the fraction or the significand or the mantissa or whatever you want to call it. Yeah, so useful thing is to talk about machine epsilon, which is like, what can you expect for the relative error when you're doing floating point calculations? It's like, there's like a little bit of slack you can't actually deal with. We've got a link here. That's interesting. Anyway, follow the links to your heart's content. Yeah, so relative error, relative approximation error when you're doing floating point stuff. So if I'm doing a calculation, and I want to know the relative error of that calculation, I shouldn't expect to get better than these numbers depending on how many bits of precision I'm using for the floating point. So these are so important that they're actually built into Julia. So you've got EPS, no, because I've imported time, it's done some weird stuff, but depending on the type, if T is a type abstract float, so haven't talked about type hierarchy in Julia, that's coming from Andy in section 4. This is basically anything that's a subtype of abstract float would be these float 64s, 32s, 16 big float. It will return the machine epsilon of floating point. Yep. So what's representable by that? Blah, 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 blah. Relative error. Again, so this is so useful that it's a function, not ESP, it's EPS. So this will default to float 64 as a thing. You can't expect a relative error greater than 10 to the minus 16, which is actually pretty good, right? Like that's a tiny, tiny fraction. Like gets worse when you're doing float 32. Remember I was talking about the Quake 3 algorithm back in lecture 1, you know, they're dealing with, if you go and look at what they're dealing with, it's 4 32-bit floats. You know, this error, relative error, is actually getting kind of big now. And then you get to float 16 and it's terrible. Like that's getting pretty bad. Cool. And that's nothing more than just this. It's like, how many bits do you have? You know, back here, back up to the top, we went, oh, okay. It's 50, hopefully 64 minus 13, counting plus 1, you'll get 52, 23, 10 for those different floating point standards floating point representations. This is on all computers. They all choose the same one. Okay. Cool. So this one, what do I want to say about this? So suppose there's a mathematical function that maps, hopefully this is leading, that's mapping the floats to the reals, and it's mapping it to the nearest floating point number in F. So this is basically just saying, like, this is just like a demonstration, the relative error is going to stay between this machine epsilon, blah, 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 blah. We've got an example of this, and I think this is super interesting. So what we're going to do is we're going to pretend that the 64-bit non-squares, so this is a good one. So hopefully you can interrogate this bit of code and work out what it's doing. So it's going to take the numbers between 0 and 100, and it's going to take the numbers that are I squared. There's a comprehension on the other side. So these are all powers of 1 to the 1 squared, 2 squared, 3 squared, 4 squared. We're going to get the set diff of those. So these are numbers that don't have an integer square root. That's the whole point of doing this bit. So if I do square root 2, you know, 1 point, that should be a stone 1, 3. But if I did square root 4, you know, that's boring. It's 2, has an integer representation. So the whole point was to get non-square numbers. And what we're going to do is going to take these non-square numbers. There's a little tilde. You can add this onto your equations if you want. We're going to do the float 32, square root of float 32, and we're going to do the square root of float 64. So the idea with this is we looked at the machine epsilon of these two. Oh, ESP, I keep typing it. EPS and float 32. The error is so much worse for the 32. It gives us an idea of, like, we can pretend that the float 64 one's like perfect. If we wanted to be more careful, we could use a big float, like we talked about big ints, you know, arbitrary precision representation. And we can get an idea of what the error does. So square root of both these ways. So I don't know how much I copied across. So this is, again, relative errors. So I'm taking the difference between these two, dot minus 1. And again, little plot thing. We'll just reproduce it to see we get the same thing. It's the first time I plotted, so it's going to be slow. But basically, we should be seeing the same thing as here. So you'll notice that between these machine epsilon bounds, oh yeah, that's cool. And then we can add in, so this plot syntax adding the exclamation mark because I'm editing the current plot. You know, it's that Julia thing of if you add an exclamation mark, it's a hint that I'm editing the data underneath. So I'm taking the scatter plot, adding some lines to it. Don't know why that was so slow. But they're just those error bounds. So yeah, it's like a little dumb verification that floating point error bounces around between this machine epsilon. So you can't, as a default, don't expect your calculations to be more accurate than the machine precision. If you're going to be super careful, you have to use bigger floats. 128-bit is supported in lots of different things. Okay, what about the pattern in that? Does anyone want to say anything about that? What does it look like? Does it look random or not quite random? Somewhere in between on this spectrum of like, oh yeah, that's the, what's up? Yeah, so this is like, this is very leading from me because we have an algorithmic method for generating random noise now here. So this is going to come up again for you guys of like, how can a deterministic algorithm generate randomness? I've talked about cryptography, and in Git, you would have seen the hashes. Like, it's really useful property to be able to generate a seemingly random thing from a deterministic input. And you would have seen setting, you can draw random numbers from Julia, you can set the random number generator, and it will generate something that's random. This is actually has a lot of structure to it, this what floating point errors do. So if anyone, you hear some crazy person on the internet going, the universe is a simulation and quantum mechanics is floating point error. It's like, it's not true because it's not random like the same way. This has long range correlations of this. It's actually a very poor random number generator looking at floating point error. But I'm going to talk a little tiny bit about machine learning tomorrow, maybe if I get a chance, or a really dumb version of it. And I just want you to think about this of like, it's a little seed in your head about how to think about how you might generate random numbers from a deterministic input. Is that even a thing that you can do? That's all I wanted to say. Cool. So you get some special values. So there's a special one for nan. So just in case that's not clear what's going on, 0 divided by 0 is not a number, which is nice to know because it depends on the limiting process. You did all the calculus to be happy to think that. This has a special value in floating point, which is this guy. They've decided, you know, all these guys are ones and then all these guys are zeros is nan. You also get inf, negative inf, all mapped to special values. So floating point numbers are meant to be the reals. You've got not a number, just for special cases like 0 divided by 0. This will bite you. This is a thing that will bite you. When you get nans, they propagate. So if I get something like nan times 0, this is like a super common bug. It'll go like, oh yeah. So if I have some equation and I pass a nan in, suddenly I've got nans everywhere and everything disappears. So being careful about dividing by 0 is like a thing you should like get a twitch over if you're looking at someone's code and they're dividing one number by another number and there's no catch for what happens when this thing gets close to 0 on the bottom line. Just be careful of that because nans going through your code is a big source of bugs. Okay, now this is fun stuff. So if we look at some special, so big is a function that will make a big float. So again, someone in the chat just said like Ep's big float is 10 to the minus 77, which is amazingly small. Arbitrary precision. So what we can do is if we go big of 0.1, it's actually not 0.1 because of this, you know, you don't get to choose what you're going to get a number that's close to 0.1, you know, there's no perfect representation of 0.1 in floating point. Now this one's my favorite is you lose like this really useful property of numbers. Like this is like, you know, real number stuff 101 is like, this is associativity of numbers, right? Like I shouldn't matter where I put these brackets. If I go 0.1 plus 0.2 plus 0.3 with brackets on the left bit, or I enclose the brackets on the other side, Why are they not the same? That's not the same. That's funny. So because of these floating point errors and the way you order operations, you lose associativity. It's not a big error though. If I look at the difference between these two, it's, again, this number, that's tiny number that's under floating point error, you know, that floating point epsilon. But you're losing associativity. Like, you can't assume that that's true for floating point numbers. It's approximately true. So you have this useful function is approx. So this will default to square root of epsilon. Oh, here we go. You guys should be understand this. Like, you've got a relative tol equals a real if a tol greater than 0, 0. Otherwise, it's square root of epsilon. So it defaults to the square root of epsilon. It's like, that's fine. If it's under that, I'm good enough. So remember that useful function. So when you're doing tests, when you're writing code and you're doing stuff with floating point and you're doing tests, you never, ever, ever expect to get it right on. You're always expecting this tiny bit of pseudo-random fluff on the top of things. It's not a big error. So yeah, just showing that. This one is even, it's like, maybe it's obvious, but it's kind of annoying. So if I'm going to add 1e 10 to the minus 9 to 1e to the 9, so we're separated by 18, 10 to the 18, and I go, does that equal 10 to the 9? It says true. It's like, okay. So that little guy just disappeared, which is annoying. I have a tiny demonstration. This is like really obvious maybe, but like all this stuff is obvious, but you kind of forget it. You kind of just go, I've got my monkey brain. I'm going, floats are real numbers. They do real number stuff. I don't expect to lose associativity, and I don't expect little numbers to disappear when I add them to big numbers. So basically, this isn't true, but it's a good mental model for what happens. This isn't actually how you add floating point numbers on a CPU, but you can think of them as like, they're just these numbers of this sort of form. We've got, you know, 1.234 by 10 to the minus 5 plus, and b equals 2.345 by 10 to the minus 3. If I want to do a plus b to equal c, the way it kind of works is you do a shift. So because it's binary, you can do a bit shift back to these early operations in section 1. You're going to shift them to the same exponent. So hopefully you can see that if you have a finite precision here, this guy's going to get marched 2 across to 0.012, 10 to the power minus 3, and this guy stays the same. So you're going to shift so that the exponents match to the biggest one, and then you just add them together. That's kind of the algorithm that they implement for addition of floating point, which explains why if they're vastly different powers, these guys just get shifted off to nowhere. So when I'm doing this guy, if I go a little bit lot smaller, we'll see how clever I was when I did this. That's false. But if you jump up by the power of 9s, then you get this problem of it disappearing. So it's when you have vastly different power orders of magnitude. This is even worse for subtraction, which leads into following section when we're talking about finite differences. This is like natural thing. What you're going to have when you're doing finite differences on a computer typically is you're going to try and estimate the derivative by a small step. You're going to look at the definition of calculus and go, so f of x plus h minus f of x divided by h, as limit as h goes to 0. That's your definition of a derivative. It's like two numbers that are really, really, really close together. You're going to subtract them and divide them by a really small number. That gets really bad as h goes to 0. Which is hopefully something you'll see in your notes. Just wanted to say that. So this gets worse if you do repeated addition. So like you have these things of like, how would I implement multiplication if I've got addition? And it's like, oh, I could just do it n times. This gets really bad. The relative error, the error grows and grows and grows. This one I say, because it is the bane of my existence, if you're doing anything numerical with statistics, normal thing to do is to do an eigen decomposition. I've got a matrix that's like this. It's like 1s, 10 by 6. And I'm going to try and do this, you know, this quadratic form. I'm going to try and do something like calculate a covariance matrix. Hopefully that's clear. If I say that, you know, this X transpose times X, I'm going to get a covariance matrix. Then if I'm going to do something like PCA, everyone familiar with PCA? Not so much. Principal component analysis? No? Okay, that'll come up. I'll do a segue into PCA because this is useful to know. Oh no, I just want the Wikipedia page, not some random blog. So when you're dealing, like normal distributions are everywhere. They come up all the time. Your central limit theorem says, you know, you add enough small things together, doesn't matter about their low level distribution, they'll end up being a normal distribution. The multivariate normal distribution, if you've got a couple of variables like a vector, normal thing to expect. A useful thing to know is like you end up with ellipses, right? So this data is distributed in 2D like an ellipse. So it's, you know, it's a bell curve in 1D. If you're doing the same thing in 2D, it's this thing. Generally, it's like this n-dimensional ellipse. Really common to have long, skinny ellipses. Like most of the variation is happening in this direction and it isn't necessarily aligned with one of the axes. That's why you do PCA. PCA is an algorithm for determining like, what's the rotation that diagonalizes my covariance matrix. Maybe that's clear. Maybe that's clear. That was really quick. I wasn't expecting to do that. So that's off the cuff. So this kind of thing is like a super common thing. If you're dealing with this, I don't know how much. So if you haven't done PCA or haven't done this stuff. So if I've got this kind of matrix, like a covariance matrix, the property mathematically I'd expect is for it to be semi-positive definite. If I say that, does people glaze over? Like, what the hell? Or is that okay? I've got one guy. You want to explain it? No, you expect all the eigenvalues to be positive. Like that's, yeah, or there's other ways of formulating it, but that's why I've done this demo. It's like, so if you think about like, it's a covariance matrix, if it's lined up with the axes, the standard deviation should all be positive, right? You can't get a negative standard deviation. That's kind of the way it works. Just the generalization of that concept is called semi-positive definite. So this happens to me like good every 6 months. I have this problem of like trying to do some algorithm and I've got covariance type matrix. I expect it to be semi-positive definite, try and do this diagonalization by eigenvalues. And what actually happens if I do that is the eigenvalues, some of them go negative because of floating point stuff. And it's actually like a good whack of them in this case are negative. So we've got 1, 2, 3 out of 7. So this will happen. And if you have an algorithm that assumes that all these eigenvalues are going to be positive, and then you plug it into your next algorithm, everything goes kaboom. Like you're going to go, the typical one is like you take a square root of these guys. What's going to happen in Julia if I do a square root of a real number? Kaboom. So this is a normal sort of bug. This is a normal mathematical analysis bug. I get this all the time. It's happened to me this year. I always think of it when I go to teach this class of like, when was the last time this happened? And it's happened to me this year again. So that's actually a sophisticated question that you can think about of like, how do you round a matrix to preserve a certain property? Like I want to, like it's easy when if I'm doing 0 divided by 0, I can add a tiny bit of small positive number to the bottom line, and then it's always going to be well defined. How do you guarantee that such and such a property of your mathematical object is preserved as you do these operations? That's actually a really hard question. So the dumb way is to go, well, if I do my eigenvalue decomposition and any is 0, you're 0 now, keep going. But that can cause problems later on too. Hard question. This happens all the time. I just feel like I have to say it because you go on, you'll do this stuff. I guarantee you'll do a simulation at some point and you go and do this thing, kaboom. Floating point. Any questions on that? Super quick. No, everyone's happy? All right, cool. We've got 5 minutes. That's enough time for numerical derivatives because this leads on exactly to this point. I was saying is like, a really like the definition, the difference between this approximation and the definition you'd see in first year or high school or whatever it is when you first start doing calculus between this is a derivative is you just put a lim as h goes to 0 on this guy, then it's exact. So you might think naively that a reasonable approximation is to go, okay, I'm just going to take a finite step in H. So if you drew it, I think I might have drawn some stuff. We can reuse this guy. So, if I'm trying to estimate this function at a point, I can take a point here on this function and fit a straight line to it. That's a reasonable approximation of the derivative. This bit I just told you about, if you add a big number to a small number, it gets absorbed. This is this behavior that will happen when you try and do finite difference approximations to derivatives. This is what this, I think, is this a homework question? I can't remember. To do something similar. This is the intuition for this, is like, if I set my H as a very, very, very small number, down under this like square root, whatever, square root epsilon, floating point epsilon, it starts to go bad in this weird kind of non-deterministic way. So if I go over this side, this is completely obvious. It's like, if I'm taking huge steps to approximate some curly function, I don't expect the finite difference approximation to be any good. But if I'm thinking maths land and it's a real number, not a floating point number, if I make this really, really small, this approximation should become exact. And it's not actually what happens. What happens is it starts to go weird in a strange way, and weird in a strange way that depends on the actual function that you're evaluating. So what's the deal with this one? Okay, so it's evaluating this function, 2x times cos x squared, where we know the analytic derivative, so we can compare the errors. And we're just evaluating it at different points. So this breakdown point depends on where you're evaluating it on the function as well. So it's not even like this universal result that you can go, well, as long as you're above blah, you're fine. It's kind of this thing of like, if you go too small, it's going to be bad. And if you go too big, it's going to be bad. And it's not obvious where the middle is. Okay. Why would you do finite difference approximations? Is because doing calculus is hard. Like, you spend all this time learning the machinery of doing calculus in your lectures. Hopefully, integration's worse, but derivatives are kind of hard if the function gets any sort of complication. Like, it's kind of tricky. Like, I've professionally spent like a good month just verifying that it was a Jacobian in that case, so a matrix of derivatives. I'm sorry, a vector of derivatives in that case. It's probably a gradient, but just verifying that was correct by finite differences, because it was hard to do the maths, right? And it's a long time to spend on something, so it better be an important problem. Something that's come recently, and this, just going to say a tiny bit about this, is that one of the cool things that it's in lots of languages now, but it was on there early in Julia. It's like super exciting for me, is the automatic differentiation. You can go off and read a lot about this, but this is, it's like, you're going to see when you get Paul Verbeek's section, when you get to that part in the course of like doing computer algebra, this is kind of a different way. It's using a special type of number to get an exact derivative to floating point epsilon. So rather than passing a real number to your function, you pass a special type of function called a dual number, and you get the derivative for free. Hand wavy explanation really quickly is it does something like the chain rule, and the squared terms are small, so it cuts them away. And there's lots of different ways. There's forward mode, reverse mode. You can go and read it. You can read the Wikipedia page on dual numbers and get very confused. If you're into algebra, you'll find this exciting. I'm not going to say it's Clifford guy. He's like Clifford Algebras. If you want to go and read some more confusing stuff, some of you will get very, very excited by that. What I'm excited by is that there's a bunch of libraries. This one's actually not the favored one in Julia now. So I wrote these notes a little bit of time ago, but I don't need the show, but what you can do is there is a function in this library, zygote, and I can pass an anonymous function to it and an evaluation point. So that's what this 0, 0 is. And it will, after you do the pre-compilation magic, so slow on the first time, but good on the second time. So this stuff is super useful for when you're doing optimization. Like this, I can't overstate how much of a big difference automatic differentiation has made to machine learning in particular. So all this stuff about like since 2014, neural networks got really good. A lot of it was to do with automatic differentiation through arbitrary computation. So I can have a really big function. Who wants to try and trick it? I don't know. I won't be able to work out what these things are quickly, but oh, that's because it's 0. How about we do it at 1? This is as fast as a single function evaluation order. And depending on what you're trying to do, for a gradient, it's good. Going the other way is not so good. If you've got Rn to 0, so doing gradients. Oh, sorry. No, this is just a gradient. What it does inside is quick. It's too late on a Tuesday afternoon. It will give you, these will be accurate to floating point without having to actually do derivatives. So this is super useful. Good thing to know. Good for confirmation if you wanted to check, like if you're doing this sort of analysis and you don't want to do the maths, if you don't want to sit there and like, you know, I'm looking at sine squared and I don't want to actually calculate this derivative, just stick it in the automatic differentiation library these days. Yeah. As long as you say, I don't mind. I would say that's fine to use this package to verify it. But again, you kind of, this is this problem someone said about computer assisted proofs early on. It's like, do you trust it? So, maybe if it's well implemented, it's fine. It's like maybe it's a good extension thing to check, or you can check it on a few functions. Cool. Any questions on that? I think that's a good place to stop. Talked a little bit about that, and then differentiation's best friend is integration. So talk about that on Monday next week. Thank you very much, everyone.